So now we're going to find the surface area of a solid, but we're going to do it step by step. So we are going to start from scratch. So we don't need this. Okay. So starting from scratch, we would create we would split this up into many strips. Okay. But let's just look at one particular strip. Let's just look at this strip here. So apparently this thing here has a name. It's called a frustum. So it has a name here. So the area here is given by 2 pi r, and this is our r here. Remember that r so our circumference here is given by this, and we are going to use the average of the two heights. We are going to use the average of the two heights. So add these two heights together, and then divide it by 2. Okay, and then later on these two will kill off each other. But then don't forget our arc. So for this one particular strip here, the circumference is given by 2 pi r here. This is our r. Okay, 2 pi r. But then this arc length here. Remember, we're starting from scratch. We're not going to use the arc length formula. We are starting from scratch for this particular interval here. So this length here, I know it's going downhill at the moment, but let's just change it. It still works with going uphill. It's easier for your mind to visualize it. So here we are using Pythagoras here. This here is delta y. This here is delta x. So the straight line here is given by this, by Pythagoras here, square root it. That will then give you this. It will be an approximation to the curve. Later on, as we decrease the width here, this straight line becomes the curve. Okay, so well anyway, the approximation is given by this, by using Pythagoras. Okay, and then these two will cancel out, taking this whole thing here to here. Okay, and then so this here is for one frustum here. So if you want the whole surface area, you have to sum up all of these. So the surface area is you summing up all of them. So it's you summing up all of these. Okay. Yeah. Don't forget there's a squared here. Okay. So it's all the way to the end, and then when we get to this stage here, we don't want this delta y here. So we would use this. We would use this. The average. Remember when we first started out doing the mean value theorem. If you have a function something like this, the average gradient that exists between the two, well, somewhere on this function here, there must exist a gradient where it equals the average gradient. That's basically what this is. This is really the mean value theorem. So the mean value theorem is really, if you have a function, the average gradient that exists between these two, well, somewhere along this function here, there must be a gradient where it equals the average gradient. So we've done this in the past before. So the average gradient, well, somewhere on the function there must exist a ck somewhere in between these two, where the gradient will equal the average gradient. Okay, so this here is your average gradient. So somewhere along here, you see, let's just say at this point here, you see at this point here, which is ck here, the average gradient equals the well, at this point here, the gradient at this point here equals the average gradient. That's basically the mean value theorem. Okay, so the thing is, we don't want this delta y here, so we would times both sides by delta x, so it equals this delta x here. Okay, because remember, if you have a graph of y equals 3x plus 1, say, so it has a gradient of 3. If you get this distance here, let's say 1 here, if you get the gradient times the across here, then you would get the delta y. Well, here, if you know the gradient, and then you can times by the across here, that would then give you the delta y. Well, the delta y equals this. We would then put this thing into here. Okay, and this is the trick of using calculus. You would introduce this ck here. You would introduce this ck here, where the ck is trapped in between these two. The trick is introduce this ck here, and then as you make delta x tends to 0, the ck becomes trapped in between the two. Well, the trick is to introduce the ck into the formula, and then later on hopefully it will become clear later on. So put this thing into here. That will then take you to here. Okay, and then so remember the surface area is approximately you summing up all of these. So hang on. So that will then take you to so from here, that would then take you to here. But I don't know how yet. Let me think. What would take us from here to here? Hang on. Let me think. Oh yeah. So hang on. Let me think. Oh yeah. Hang on. Let me think. Oh so when you're here at the moment, what you've got here is delta x, and then don't forget you've got delta x here. So you've got a block timesing another block, and then here you've got this block, and then squared. So really you've got f prime of whatever here, and then you've got f prime block, and then you've got delta x times delta x. So really delta x is in common, delta x is in common. You can factor out the delta x squared here. Okay, so factor this out. So it becomes this delta x squared, and then bracket 1 plus f prime of ck. So basically just factor this out. So now you've got one block multiplying another block. Okay, and then well here if you have square root a b, that equals root a times root b. So you can break from here, you can get to here. Okay, and then this becomes this. Okay, and then blah blah blah. Hang on, let me move this. Hang on. Oops. So this thing here. Hang on. Let me just. So you've got a delta x here. So this delta x goes into here. Okay. And then. Oh yeah. So now the surface area at the moment is approximately this whole thing here. Okay. So now take the limit. Hang on. Let me just try and move this across right there. Okay, so I'm moving it across slightly. So at the moment the surface area is approximately this whole thing here. So now take the limit as n tends to infinity. Then this thing here becomes f of x. Remember our diagram looks something like this. We've got something like this. Our diagram looks something like this. So this is the tall radius. This is a short radius, and then as you make delta x tend to 0, well, when you make n tends to 0, when you make n tends to infinity, delta x tends to 0. So this f of x k minus 1 will become f of x, and then this thing here, this line here, as you make delta x tend to 0, then this radius here becomes f of x. Okay, so well anyway, that then becomes that, and then this thing here becomes f prime of x as you make delta x tend to 0. So that will then take you to here, and then from here, really we should jump from here straight to here really. But you can see that this thing here tends to this thing here tends to this, and this thing here tends to this. Well, actually, it's actually this thing here tends to this thing here. Okay, and then hang on, let me move it across. So the overall the surface area is given by this. Okay, so we were here. When you take the limit as n tends to infinity, we should jump to here. Okay, and this is what we had earlier. 2 pi r, where r is the well, anyway, it becomes this.